Okay, my name is Huolin Xin. I'm a professor at UC Irvine. So today I'm going to share with you the work about how to correctly introduce a multi-component effect into stoichiometric layer oxide, such that we don't actually introduce a lot of lithium cation mixing, so we can preserve the high specific capacity and high energy density. At the same time, we eliminated cobalt, we reduced the nickel content, and we prescribe a chemomechanical stability to the cathode, in particular a zero strain property to the cathode material. So, well, I guess for this audience, I don't really need to talk about why you need to eliminate cobalt, but I do want to make a comment on nickel. So basically, if you look at a government target that you want to electrify 1/3 of the transportation sector by 2033, that means annually you need to actually produce about 3 million tons of nickel or cobalt if you don't eliminate that. So today's nickel production annually is 3 million tons, right? So that means if we don't reduce nickel, so we're gonna have to increase the production of nickel by a factor of 2. That's gonna really produce a problem in terms of the economy and how much nickel price will go up. Just empirical evidence is that if you look at cobalt price, if you follow that, you found that 2 months ago, cobalt price actually plummeted, actually dropped to almost to the price of nickel, whereas nickel didn't actually go down. That's because portable electronics, actually the demand for that dropped significantly after the pandemic, whereas our demand for electric vehicle will only go up. All right. So I'm going to cut to the chase. Reducing nickel and eliminating cobalt is really a challenging task because nickel and manganese 4+ and cobalt are the only 3 elements that don't have significant intermixing with lithium. So basically, if you introduce any other cations other than nickel, manganese, and cobalt, you're going to basically block the lithium channel, and it's going to reduce the discharge capacity, right? There are other benefits of the cobalt. I'm not going to talk about that, but you can replace cobalt by nickel, as everyone is doing. It actually gives you higher discharge capacity, it gives you higher voltage and a higher specific energy. But the thing is, it will actually introduce a thermal and chemomechanical instability to your cathode material. So here's what I mean by thermal instability, right? So basically for layer material, as soon as you take lithium out, this material becomes thermodynamically unstable, right? So here's showing the measurement, differential scanning calorimetry measurement of at what temperature the charged cathode will undergo this exothermic oxygen release reaction. Is basically a metric for the thermal stability or the safety of your cathode material. And if you look at that, the 532 or 523 is actually the most stable one. That's why actually many EV makers still actually use 532, although it's very expensive. And 811 is 150 degrees Celsius lower. Is really actually, in my opinion, unsafe to use in EVs. And if you go down to lithium nickelate, it's another 100 degree lower, which is really unsafe. I think scientifically, the question that's worth asking is why lithium nickelate has such a low thermal stability. So next, so here's Operando XRD experiment observation that was done by Jeff, who's sitting in the audience. So not only recently, but also 20 years ago. So this is an update that he gave recently. So basically, so he showed that this plateau at 4.2 volt is related to the H2 to H3 two-phase transition. Right? And you will find that the 003 spot, as you go through this plateau, will actually bifurcate. And this bifurcation doesn't happen in, for example, A11 materials. The question that's worth asking here is, what is this mysterious H3 phase? Now, how is it related to the thermal or electrochemical instability of this ultra high nickel content material. So we perform electron microscopy study of the so-called H3 phase, mysterious H3 phase in lithium nickelate. So what we have found is that in this mysterious phase, a large fraction of it actually appear as this O1 or H4 phase. That is actually a stacking faulted phase. It basically has an interlayer shear. Such that the oxygen lattice actually follow a AB-AB hexagonal close pack stacking. So what we have faund that's different from the conventional wisdom is that the conventional wisdom says these stacking faulted phase should appear as stacking faulted slabs, right? But what we have found is a lot of these O1 phase actually are appearing as nanodomains or domain patches that has intralayer grain boundaries or domain boundaries between the O1 and O3 phases. And this does not only happen in the charged state. A lot of the O1 phase will actually be preserved when you discharge it. That actually is related to the fact that the O1 phase has smaller interspacing, so it will be much difficult for it to actually intercalate. And also electrically, this phase is much less conductive. You can almost view it as insulator. So, well, that aside, I think a question that's worth asking is the O1 phase or the H4 phase actually present in A11 material that's charged 4.4 volt? If you ask any wise person in this field, they will tell you no. The reason is that you don't see it actually in XRD, even in the highest resolution XRD. However, we perform TEM study to look at local area. We actually find a lot of, well, not a lot of, we actually find some O1 phase that's actually showing up in A1 material that's charged 4.4 volt. And that's very more interesting. There's actually two intralayer, phase boundary motifs. That's actually one is abrupt and the other is actually continuous. This is related to actually the residual lithium content that's on the two sides of the phases, right? So, but the question here is that actually by our estimate that this O1 phase only appears less than 1% in this A11 material. So is it really important to actually, does it really affect your thermal or electrochemical stability of this material? I hope that in the next two slides, I will convince you that it does. Right, so we performed a in situ study of this material while we heat it up at elevated temperatures, basically to look at the chemomechanical degradation of it. So because of the power of TEM, we can actually see the phase transformation at atomic scale. So transforming to disordered rock salt, disordered spinel, and then rock salt. These are not new, right? You can tell that by in situ XRD experiment. Right. What's really interesting is that we found a previous N-Fong two-step atomic process. That is the O1 phase for you to actually lose oxygen and become rock salt. First, the nickel will hop down into the lithium layer, and then it shear into the rock salt phase. Right. This is actually confirmed by the kinetic barrier calculation that shows the O1 phase has a lower barrier for nickel to hop into the lithium layer. So what does it mean? It actually means O1 phase actually is kinetically faster to lose oxygen, right? So they will serve as nuclei for oxygen loss, right? So this is basically the conclusion for that is that by our estimate, although O1 form less than 1% occurrence, right? It is kinetically faster for this phase to have cation mixing and lose oxygen. Right, and the other thing that I haven't talked too much about is the large C-axis difference between the O1 and O3 phase will result in the mechanical fatigue in this material. Right, so with all of the previous fundamental study we did, I think we arrived at three degradation mechanism we actually need to suppress or eliminate in order to actually make a commercially successful zero cobalt cathode. So the first is basically we need to minimize the volume change for charge discharge, right? We need to minimize the A over C anisotropic breathing such that the particle wouldn't fracture. We want to make the surface more robust to corrosion so you don't have very thick rock salt buildup, right? And the third thing is really about the chemomechanical coupling that I showed previously. So that is, you have to suppress or delay the O3 to O1 phase transformation or the H2A3, depending on which what you use, right? And you have to improve the oxygen retention. Only if you meet all three criteria, you can make a commercially successful cathode. Right, and of course, what are the metrics that I'm constrained to actually work with? I want cobalt-free, I want reduced nickel content, I want a high specific capacity higher than 200 milliamp hour per gram, I want high specific energy higher than 800 watt-hour per kilo, I want high thermal stability, right? So I want my material to be more stable than NMC 532. I want high charge rate, no volume change, reduced anisotropic breathing. I want reduced transition metal dissolution, less crossover. I want the surface to be robust, but at the same time, it doesn't need surface coating, so it reduces the manufacturing costs. Of course, the last metric is long cycle life. Of course, safety and the cycle life are the two things I think all EV makers mostly care about, right? No matter whatever you put into the third is cost. Right? Okay. Right, so this is the last fundamental slide that I'm going to show you. So if you talk to any mechanical engineers and you say that you're going to strain a ceramic material more than 1% of strain, they will actually tell you this thing will fracture. But I'm going to convince you that in this in situ movie, and it's a little bit difficult to see, right? So this is basically a piece of lithium nickelate, a ceramic cam material that we're in situ delithiating it. As we delithiate, you're seeing these dislocations that form in pairs, and they will multiply and they will annihilate. This is basically the H2, H3 phase forms that are propagating into this material as you delithiate it, right? And for this to actually appear, this material, if you have H2A3 phase transformation, that's actually more than 7% of C-axis contraction, right? And this material is supposed to fracture, if you ask any mechanical engineer, but it doesn't. So what really make our CAM materials very special is that our CAM ceramic materials are not just the traditional ceramic material. They're mixed ionic electronic conductors, right? So a lot of its behavior is more close to metal rather than ceramics. So they're not just brittle materials anymore, right? So with that gives me inspiration to actually borrow the high entropy alloy ideas that's basically being used for many years in the metallurgy field, right? However, I run into a problem, right? The experience tells us the higher nickel content, the better, right? So the more specific energy, right? So that means lower entropy is better, right? That's just empirically telling me. And also, there are a couple studies that showing high or these equimolar high entropy oxide actually only can discharge to about 80 milliamp hour per gram, right? In my opinion, this is a failure, a negative results. Fortunately, there are scientific reports you can publish negative results, right? So, but if I work on this, my program manager will tell me to stop, right? So, but the thing is, we can utilize this multi-component effect to increase the strength of material and suppress the formation of dislocation that I show you by utilizing the solute drag and pinning effect. And the other thing is reducing diffusivity that will suppress phase transformation, right? So with that, we propose to actually introduce a multi-dopant or compositionally complex doping to introduce the cocktail multi-component effect into the cathode material, right? And each dopant, by our experience, shall be introduced at lower than 1 to 2% level, So that will minimize the lithium transition metal cation mixing. The third is that we can actually increase the total dose of a dopant up to 7%. And we hope we can, right? With that, this is our design formula. This is an 80 material, manganese 13%, and we have 4 types of dopant. And what you can see is the titanium, niobium, and molybdenum actually segregated a little bit on the surface. Their concentration increased by a factor of 2 or 3 compared to the bulk. That is good because titanium, moly, and niobium are corrosion resistant, right? What about the structure? It's still a layer structure, right? So because of this segregation, the surface has some cation mixing, right? But not enough to actually increase the polarization of this cathode. And through XRD refinement, we found the lithium transition metal cation mixing is only 2.1%. This is only slightly higher than the commercial A11 material, right? So that's good. And then, of course, the true test is discharge capacity, right? Our discharge capacity is 210 million hour per gram. First cycle Coulombic efficiency 94%, always higher than A11. Specific energy 800 watt-hour per kilo. And through CV or DQ/dV measurement, you can see the H2 to H3 phase transformation, which is the detrimental phase transformation, is reduced and delayed, right? So these are all the good stuff. And I said this material is a fast charging material. So it can actually deliver at 5C charging and 170 milliamp hour per gram, right? So this is actually more than 80% of 0.1C charge. And this is not only at 3 milligram per centimeters of loading, we actually increase it to 15 milligrams per centimeter loading, which is commercial loading, that we can deliver 162 milliamp hour per gram. So basically showing the limitation of this material is not a conductivity, electrical conductivity, ionic conductivity, right? It's really about how well you can make a cathode, right? So any of the industry people here can make a better cathode than I can, right? So in terms of cycling, 85% capacity retention after 1,000 cycles in coin cells. Full graphite cell in coin cell, 98% capacity retention after 250 cycles. So in single layer pouch cells, right? So this is cycling to 1,200 cycles, 90% capacity retention. The projected lifespan is more than 2,500 cycles. So really, I want to emphasize safety is the most important thing for our EVs. So our cathode material, the NAT materials, delivers a thermal stability that's almost the same as 532. Right, so as you can see here, right, so although we have 80% of the nickel content, no cobalt, it's almost as good as 532, and this is validated by oxygen release measurement that shows our materials actually has oxygen release peak that's 100 degrees Celsius better than A11, right? This is really good in terms of thermal stability and safety. And I call this material a zero-strain material. The reason I call it zero-strain material is that two-part. The first is if you really look at the unit cell volume of this material as you charge to 4.3 volt. So the max to minimum change is actually less than 0.2%. So by our field's definitions, 1% is max to mean is called zero-strain, right? So I'm way below that. And also, if you look at the delta A versus A and the delta C versus C, right, and compare it to the baseline, which is the A11, is that we actually can suppress the A expansion and, the A contraction and C expansion by at least a factor of 2. And both of them are below 1%, right? So because of that, I can definitely call this material a zero-strain material. And of course, and as you delithiate it, this is an in situ TEM study that basically shows there's much less dislocation that's formed in our NAT material compared to lithium nickelate, right? there's a great reduction in dissolution, although our material is not coated. There's no coating, and the commercial A11 is actually coated. So the dissolution that's measured on the counter electrode is much less. At higher elevated temperatures, this our self cycles well, really high initial Coulombic efficiency, 94%, and it overtakes the A11 material very quickly after only 30 cycles. So you may ask me, are the 4 dopants some special dopant you chose such that you prescribe this zero strain property? And I can answer you by this experiment and tell you no. So we actually choose completely 4 different dopants: aluminum, vanadium, chromium, zirconium, right? And at the same time, you can see that the A and C lattice expansion and contraction are reduced to much below 1%. So this is actually not related to this 4 different dopant, the type of dopant we chose, but rather this is multi-component effect that are actually employed, right? That's really novel. So what about lower nickel content, right? So I mentioned that, right? So we developed an N50 materials, a lot of them manganese and those dopants. It's a very safe material. So it's actually, the thermal stability is actually 50 degrees higher than 532. And also it's cheaper. The energy delivery is higher, right? So this is really good. It's very safe, very cheap. And again, it's almost a zero strain material, right? So the volume change as well as the AC change are a little bit barely above 1%. So the multi-component effect is still suppressing the strain evolution, right? In terms of electrochemical performance, we can deliver 700 watt-hour per kilo for this, this cathode material. It cycles much better than 532, right? The voltage phase for this material is much slower, right? This is really a, a key point for high manganese material. You worry about the specific energy actually drop. It's actually very flat. And we put it into a pouch cell. This is 95% capacitor retention after 1,000 cycle. And the projectile cycle life is higher than 4,000 cycle. This is really a high manganese and low nickel cathode that can compete with lithium iron phosphate, both in terms of cost as well as electrochemical performance and safety, right? So in my lab, we can make those material at 250 to 200 grams per batch, and it almost perform as well as those small batch synthesis. So a little bit of the future, right? So we're making these material into single crystalline form to further increase its electrochemical performance. And also, one of the reasons I create this zero strain material is really to use it in a solid state battery when you have hard contact, right? You don't want any fracture, any delamination. And it works really well. So this is still low loading, 0.6 milliamp hour per centimeter square, but at 1C, so this is 0.6 milliamp. It's not small current that most people do, like 0.2, we do 0.6. And here you can see can cycle up to 36,000 cycles, right? At 3,000 cycles, 70% capacitor retention. This is fantastic, right, for solid state, right? So basically, in summary, we have a solution that is a compositionally complex doping strategy to solve the following 2 questions. The first is how to introduce enough dopant strengths without changing the host crystal structure. In our case, it's the layer structure. You don't want intermixing. How to universally reduce strain and suppress phase transformation. You basically follow our recipe. It can actually work for any intercalation cathode, right? So a little bit more, right? So the question is, can we actually dump any dirt into intercalation cathode? Well, yes. We already found that we can actually use those low purity ACS reagent, 98% purity chemicals feedstock for layer cathode. We synthesize. It doesn't make any difference, right? So we're dumping dirt into it, basically. But no, is that if you ask me, are the 4 dopants I chose the best dopants? My answer is no. And it also depends on what dopant you want to find. Do you want to find the most low-cost dopants, or the highest performing in terms of discharge capacity or rate? So we got to use calculation, experiments, ML to actually guide us to find the one that you need. Right. So with that, I'm going to end my talk by thanking all the sponsors and all the collaborators who have contributed to this work. And thank you very much for your time and attention.
The floor is open for questions.